cases, there were limitations on that. Down the slower end of the frequency, noise to signal ratio became a problem, just because the waves were so small. And up the top end of the frequency of motion, so when you're moving the fastest, the radiated waves become, the harmonic radiated waves become quite short, and that means the accuracy of the placement of my sensors in that pond becomes an issue and affects how well the model's going to relate, and that basically gives you an upper limit on how well I can match the models. One of the things to notice though with the heaving body, there was some harmonic waves radiated, so sort of harmonic frequencies of the motion, whereas in the sphere case there was actually quite a high content, up to sort of 30 or 40% of the radiated energy was happening in harmonics greater than that, greater than the first. So if you're bobbing up, surging the plate backwards and forwards with one frequency, you were getting waves coming off at 2 or 3 times the frequency, considering which was a large amount of the power radiated. So there was a lot of losses going on in that situation. And so this answers the question of how much power can you radiate. So this is the plot for the heaving sphere. You've got the frequency of motion, which effectively controls your wavelength across the bottom, and the 500 millimeter sphere, so a sphere about this big, moving up and down just over a foot, radiates 12 watts. And yeah, that was the it wasn't the peak I registered. I think the largest I registered was 17 watts for a larger motion. But I've got plots for the heaving sphere, surging sphere, and the heaving cylinder that all sort of match well.
Do you know what the electromechanical power input is at that point?
No, I don't. I can tell you it was a 300 watt motor being run off a 500 watt motor being run off 24 volt power supply, but it wasn't drawing anywhere near that. So yeah, that was perhaps one of the biggest criticisms of what I was doing, because I didn't have an easy way to measure that.
So if you did have that, then I mean that would give you some information about the conversion effectiveness, right, of that shape, right?
Yep. I've developed some theory around that in the next other sections. It actually brings us to so what are the limits on wave radiation? We've already seen a couple of them. We've seen wave breaking and turbulence. If a good wave radiator is a good wave energy absorber, the limits on wave radiation there should be the limits on wave energy absorption. So understanding what those limitations are should give us an insight on how to design our devices. You've already pointed out we'd really like to know which is the most efficient radiator, or which is the best device for wave radiating. We've sort of seen already that the cylinder isn't any good, but was that just a choice in scale? Have we just chosen the wrong scale of device? What do we mean by an efficient radiator? If there's an efficiency, is there a maximum efficiency? Is there like an upper theory limit where you can approach, like there is with wind turbines, there's this theoretical limit and try and reach that? And so those are questions I wanted some answers to. And so went back to the theory and applied the circular control volume again. So I said, okay, started off with a cylinder. So if we have a cylinder bobbing up and down, that's going to cause, as it bobs up and down, it's going to displace a volume of water and push it out the sides of water, which is then going to radiate the wave. And equally, when it pops up, it's going to suck water in and sort of create the other part of the wave. And so with the theory that we've got in terms of circular waves, what we can do is say, okay, well, if we let this area be dominated by the body and the outside area be dominated by the wave, if the wave is moving this much water backwards and forwards, we can say, well, what's the type of wave that sits on the outer field that moves exactly the same amount of water backwards and forwards, and try and match the two up together. And so this way we can relate the volume displaced by the cylinder to the volume displaced by the wave as it moves backwards and forwards, and therefore try and couple the two together. This works well for a cylinder, But what radius do you choose if you've got a sphere or some other sort of axisymmetric shape? And so what I've come up with is this concept of a characteristic cylinder. So this is a theoretical wave radiator, and it has the same displaced volume as the sphere in this case. It has a certain radius and a certain depth, and it represents an ideal radiator. So all of the displaced volume is equated to a radiated wave. There isn't any sort of near field effects, so you're not looking at sort of water that kind of travels just up to the surface and then back, or is dissipated, sort of involved in turbulence. It's purely a theoretical concept of what the maximum efficiency can be. And what we find with that is, we've been talking about this displaced volume. We find that there's a relationship between the displaced volume and the height of the radiated wave that you can create with that. So as the amplitude of the wave goes up, you require to move more volume out of your control, more volume of water out of your control volume to be able to model that, or to generate that wave. One of the other limits that we've seen, which we've already talked about, is the wave breaking, which we saw in the sphere. And I went back to the linear wave theory and looking for a wave breaking criterion. And basically they fall into 3 categories, which was kinematic, geometric, kinematic and dynamic. And the geometric and kinematic, the geometric condition is based on wavelength to wave amplitude ratio, which is kind of not that useful for us because the wavelength does change a little bit with the Bessel functions, and so does the wave amplitude as you go further out. The kinematic wave breaking criterion is basically it basically looks at the particle velocity at the top of the wave. So when the particle velocity at the top of the wave is moving faster than the wave itself, waves should break. However, experimentally this doesn't quite work out, and people have measured faster velocities at the tip of the waves than the wave is travelling, and all sorts of stuff. So generally didn't work out too well. So I ended up with the dynamic wave breaking condition, which is at the top of a wave, the acceleration of that point must be some factor less than gravity. So it must be greater than the factor of gravity to cause breaking. Theoretically, when you look at Stokes waves, which isn't quite linear wave theory, but the factor, the fudge factor, turns out to be 0.5. Experimentally, it does actually work out to be somewhere between 0.33 and 0.52, depending on whether you've got wind or whether you're looking at regular or irregular waves. And it's also something which you can apply quite readily to the circular wave theory. So you can look at the acceleration at the point at the peaks and calculate what that is. What that allows you to do is draw 2 lines on the radiated power graph. So the line on the left here is your displaced volume limit. So because the amount of displaced volume limits the amplitude of the radiated wave, it also limits the power that you can radiate. On the right hand side here, you've got the theoretical breaking limit based on that dynamic breaking criterion, which, to be fair, there's actually no basis to applying this to a circular wave, but then again, there's no other research that I found, and if you know anything else, it would be great to hear from you. There's been no research into radiated waves and how they break. The interesting thing about power curve is I've plotted here the heaving sphere. So I've taken the sphere's dimension, calculated my characteristic cylinder, and then calculated the displaced volume and the wave breaking limit based on those 2 factors. And down at the low end of motion, the sphere matches pretty well. That's about the best I could hope for experimental work. But the interesting thing is that we're getting a tapering off significantly earlier than expected. And I reviewed all the video of what we were doing, and sure enough, this point here is where wave breaking initiates. So what we're seeing is that in the circular wave in the generation of circular waves by a sphere, we're getting breaking significantly earlier than theory suggests it should be possible. Now that may be that the theory's wrong, or maybe that there's something about the shape of the sphere that's promoting wave breaking, but that's something to be looked at in the future. We can plot the same graph for a surging sphere, and you can see that we don't quite get as good a correlation as we did for the heaving sphere. And this is largely because with a surging sphere you actually get what is known as self-circulation. So as you surge forward, the displaced volume that you're calculating isn't actually all of the water involved in the wave that radiate forward, because what happens is that sort of the water builds up on the face of the sphere, and then all the rest of the water is just pushed around the sphere out the back of it. And so you're not actually getting as much water involved in the creation of a wave, because it's just circulating around the device, around the sphere. And so that's the most likely reason why these two don't match up. But that's a really good thing to consider in terms of sizing a surge device, is that you have to be conscious that if water's going to flow around, you're going to be losing conservative efficiency.
Question.
Yes.
What's contributing to the large air bars?
The large component of that is location of the sensors amplified through the fact that it's a power calculation.
Okay.
The biggest thing with that is the matching. So we've related the accuracy of the matching to an error, and that gives you an error on amplitude. And because power is a square relationship with amplitude, it ends up being quite a big error. The conclusions from that section of things is that the characteristic cylinders can be used to displace predict the displaced volume limit for heaving bodies. It works really quite well. However, more work needs to be done in the case of surging bodies with the flow around it affecting it. I mean, it might offer an upper limit or an efficient theoretical maximum for them, but the practicality is that we're nowhere near that, so we need to look at that some more. And it's quite clear to see that the radiated power from heaving sphere is actually being limited by this wave breaking. And one of the questions is, okay, well, if the sphere is not so good, what other shapes can we use to get a good radiation shape? Or is there something we can do to the sphere? Perhaps an ellipsoid bobbing up and down in that direction might be better. That's all to be worked out in the future. But that coupled with the knowledge that the cylinder isn't so good, at least we know what we're looking for in terms of a body that doesn't induce wave breaking, yet still displaces a good amount of volume so that you can radiate a big enough wave to absorb some significant power. So this is really just a summary of all that I've been through, and I was more for the thesis side of things. So yeah, just looking at the developed wave theory of circular waves, deriving the expression for absorbed power, also deriving an expression for the group velocity, which is still quite complicated and wouldn't cooperate with fitting on a slide, so I haven't included that equation. And also given the optimum conditions in terms of wave energy, in terms of wave conditions, and this is different from what's been done before, where optimum energy absorption is given in factors of hydrodynamic characteristics of the body, which then have to be determined experimentally. So this just looks at the wave radiation side of things. The experimental technique and analysis method work quite well for matching and recording waves. There's still plenty of work to be done there. There's a lot of data that I've recorded that hasn't been looked at, which I did compound motions, so sort of surging and heave together. Preliminary results are, it looks like that you just sum the two of the individual cases, and that's about what you get in terms of radiated wave. That's just preliminary. Still a lot of work to be done there. And the method I've proposed of creating this characteristic cylinder or an ideal radiator as a benchmark for the peak efficiency